sekali lagi. Good morning, everyone. We are from Group 2 presenting our project titled Finite Element Analysis FEA on a mountain bike frame. Okay, next slide. Okay, FEA simulation overview. This project used analysis to simulate the structural performance of a mountain bike frame made of aluminium 606-T6. We evaluate the frame under three real-world riding conditions: flat terrains, uphill climbing, downhill descending. The key parameters we focus on are von Mises stress, total deformations, factor of safety. Our goal was to assess the strength, stiffness, and safety margin of the frame. All right, next. Next slide. All right. The downhill directional deformations. Under downhill loading, we observe the maximum deformation is 0.0345 mm. Minimum deformation is negative 0.085 mm. So the total average deformation is only for 0.0026 nm. These values indicate that the frame maintain excellent stiffness and show no excessive bending even under demanding loads. Okay, next slide. Okay. Okay. Downhill equivalence elastic strain. The maximum equivalent elastic strain was 0.0027 mm, which confirmed that the frame remained within the elastic limits. This means the material can fully recover after loading. No permanent deformation occurs. Okay, next slide. All right. For the von Mises stress, downhill, the maximum von Mises stress was 16.91 MPa, far below the yield strength of aluminium, which is 276 MPa. This shows that the frame is structurally sound, even in the harsh downhill conditions. Okay, I will pass my next slide to Vina.
Hello everyone. Now I'm going to present about downhill safety factor. And the minimum safety factor recorded was 7.6649, while the average and maximum were capped at 15.0, which is an upper display limit. So even the most stressed region of the frame is over 7 times stronger than necessary. This is our critical loading for downhill. Among all scenario tested, downhill riding is identified as the most critical because of: first is higher seat load, which is 850 Newton. Next is braking force on handlebars, 200 Newton horizontally. Lastly is additionally 100 Newton vertically force on the handlebars. The combination creates complex and high stress in areas like the rear triangle and the bottom of the bracket. Next is about our parametric metric study. This is our frame of the diameters. We also performed a parametric study to test how to reduce the main tube diameter affects safety. And this is our key findings. At 24 millimeter, the diameter, safety factor is still acceptable, which is 2.42. And at 20 mm, the safety factor drops below 1.0, which is indicating a potential structural failure. Therefore, the recommended minimum diameter is 24 millimeter or above for safe downhill use. Next is for the conclusion and our future work. The aluminium 6061T6 frame design has a high strength and reliability. Next is all stresses and deformations are well within the safe limits. Next is stress hotspots like the bottom bracket and tube joints could benefit from reinforcement. The last is the parametric study proves, which is we can optimize weight without compromising safety. For future work, and we propose refining the frame geometry for better stress distribution. Second is exploring alternative materials or composite hybrids. And last is simulating dynamic fatigue over time to improve durability. Thank you.